Okay, so we're taking hydrofluoric acid and we're mixing it together with a solution of sodium fluoride, and they're asking me to calculate the pH of this resulting solution. They gave me some info here, like some starting volumes and starting molarities and the Ka of the hydrofluoric acid. So, well, I know hydrofluoric acid is a weak acid, and I know how to calculate the pH of a weak acid. I do a Ka ice chart, calculate X is H, and I take the negative log with that. But now I'm mixing it with a solution of sodium fluoride, which is a salt solution. And I know sodium is going to be neutral because it comes from sodium hydroxide, something strong. But that fluoride is going to be a basic ion, and it's going to affect the pH. So what happens when I mix these two things together? How is it possible to calculate the pH of this overall solution? I like to start by drawing a picture and getting a feel for what we have in solution, writing down all the information, deciphering this question, breaking it down into little pieces. So we're taking 100 milliliters of a hydrofluoric acid solution. It has a molarity of 2 molar. And in solution, I know it really looks like a bunch of HF molecules stuck together. I mean, not broken apart into ions, and very few of them are broken into ions. Very definition of partial dissociation, that is what makes HF, hydrofluoric acid, a weak acid. For the sodium fluoride solution, it is also a starting volume of 100 milliliters. It has a molarity of 1 molar. It is an aqueous ionic compound, 100% dissociation into fluoride and sodium ions. Of a salt solution, I know that the sodium comes from something strong. It's going to spectate here. It's going to be neutral. So essentially from here on out, I can pretty much ignore the sodium ions. And the only thing that affects the pH at this point is the fluoride ion. So when I mix it all together, I know that the 100 plus the 100 mils is going to give me a total volume of 200 mils. And I know that the fluoride ions are going to be present in the solution, and then the purple beaker, the weak acid, hydrofluoric acid, is going to be present as well, and a very small percentage of those are dissociated into ions. And the question is asking me to solve for the pH of this solution. Well, I know pH is the negative log of the concentration of H+. And I'm looking here, well, I know the concentration of H+. It came from the hydrofluoric acid. But you have to keep in mind that hydrofluoric acid really dissociates in water to produce hydronium and fluoride negative. Or in other words, if I omit the water and write the simplified equation, which you're welcome to do, it produces H+ and fluoride ions. Keeping in mind hydronium and H+ are the same thing. So I'm looking at my dissociation equation for hydrofluoric acid. This new solution that we've created has some molarity of HF, and it has some molarity of H+, has some molarity of F-, and how am I going to figure out the concentration of H+? Because if this is a regular Ka ice chart, I just start with the initial HF, and I go to town, X squared over the initial concentration of HF, boom, solve for X, and you got H+. However, what makes this problem a little bit more difficult is, not only do you have a concentration of HF, you also have a starting concentration of F- because of these green fluorides that came from the salt solution. So it's not going to just be X squared over your initial HF concentration. Rather, there is an initial concentration of the fluoride ions. But just like with HF, where we're ignored to allow the minus X, and the equilibrium concentration of HF is going to be the same as the starting, we can do the same thing for the fluoride, because fluoride ion concentration at equilibrium is going to be about the same as the starting concentration of the fluoride ions. And that's because there's very little dissociation of the hydrofluoric acid into fluoride ions. So what do we have here? We have weak acid dissociation equation, which I can write as my Ka expression. And now I need to plug in all the numbers. I know the Ka, that was given to me. It is 7.2 times 10 to the negative 4. I don't know H plus, that's what we're solving for. But there is a way for me to calculate the concentration of fluoride and the concentration of hydrofluoric acid. And it is not the 2 molar and not the 1 molar. I can't use those molarities because I need to know the concentration of fluoride in the new solution and the concentration of hydrofluoric acid in the new solution, the resulting solution. So I have to calculate the new molarity of HF and F minus in this new solution. Well, if I look at where all the HF came from, it came from this 100 milliliters of a 2 molar HF solution, and we have doubled the volume up to 200 mils. So what does that mean for its molarity? Its molarity gets cut in half. Or in other words, I'm doing M1V1 equals M2V2, but I'm doing it all in my head. I'm using a little mental math, a little bit of logic. If I double the volume, my molarity should be cut in half. So the molarity of HF is going to be 1 molar. I'm going to think about the same thing for fluoride. Fluoride also started with a volume of 100. Its volume is now double its original, so if I'm doubling the volume, again, my molarity is going to be cut in half. If I look at the original molarity of the fluoride, it was 1, so now it's just half of that, 0.5. And again, I am ignoring the sodium because I know the sodium, yes, if it makes you feel better, you can draw the sodium in here if you want to, but you know that it's really not doing anything. It's spectating because it's neutral, not participating here, not affecting the pH at all. So the molarity of the sodium fluoride is 0.5, and essentially that is the molarity of the fluoride. But anyways, now I got the new molarities of your diluted solution. Those are the molarities you want to plug into your Ka expression. So I'm going to plug in 0.5 for fluoride and 1 for the hydrofluoric acid, and you're going to solve for H plus. 1.44 times 10 to the negative 3rd molar. So pH, we said, was negative log of H. That P means negative log. So negative log of 1.44 times 10 to the negative 3. .84 is the pH of this resulting solution. So if I look at this solution, really examine the particles in it, I have HF and I have H plus, and I got a little bit of F minus coming from that weak acid. But then these green guys, that's fluoride ions. So what are the two major components present in the greatest quantity in this beaker? HF and the green F minus. Okay, so the two major components, HF and F minus, you have to think to yourself, how are they related to one another? Do you recognize that as a conjugate acid-base pair? Okay, so when I mix together this weak acid together with the sodium fluoride that contained its conjugate base, I created this conjugate acid-base pair together. And I know that the HF and F minus, they're not going to react together because they're conjugates of one another. And conjugates don't ever react together because they're always on opposite sides of that arrow in the balance equation. One is always a product of the other. So what we have created here is something known as a buffer. Anytime you have a weak acid in solution with its conjugate base, I'm not talking about the conjugate base that comes from it dissociating, but that conjugate base that came from something else, another solution, like our sodium fluoride in this case, you've created a buffer. Likewise, we could have created a buffer using a weak base and then adding in a solution that contained its conjugate acid. Key here is that you have a conjugate acid-base pair together in solution. That is what makes a buffer. And the cool thing about a buffer is that it resists a very, very significant change in pH. Meaning, since our pH of our buffer is 2.84, it's going to stay at about 2.84 no matter if you add acid or if you add base to the buffer solution. And that's because the buffer contains two parts. Our buffer contains HF and its conjugate base, F minus. Okay, I'm drawing a very simple picture here, just a few particles in solution. And what I mean by resisting change in pH is, let's say we add in some hydroxide ions, for example. In come some hydroxide ions. Maybe it's sodium hydroxide, lithium hydroxide. Either way, all I care about is the hydroxide. I know hydroxide is base. And we can call him our invader ion because he's invading this solution. He's coming in as an outsider. Once that hydroxide hits the water, the hydrofluoric acid is going to attack it. And when we say attack, we really mean neutralize. It's going to neutralize the hydroxide. In this acid-base reaction, you're going to produce water, you're going to produce fluoride ions. As long as we don't add too much hydroxide, we're always going to have some extra hydrofluoric acid left over. So since we'll have some hydrofluoric acid left over, okay, you're going to have excess, and your sodium hydroxide is your limiting reactant, you're going to still have hydrofluoric acid in solution, and you're still going to have fluoride ions in solution because you didn't use any of it. Actually, you have more of it because you end up making more of it. You still have a buffer, and that pH isn't really going to change much. But let's say we add in some H+, which I know is acidic. Well, it's an acid. And we can label him as invader. And he goes. And so to this buffer solution, when we add H+ invaders, it's not the acid that attacks it, but rather it's going to be your conjugate base that attacks the H+. Makes sense. We have to have an acid-base reaction to make HF. And as long as we don't add too much H+, as long as we keep it the limiting reactant, the fluoride is going to be in excess. And you're still going to have some hydrofluoric acid. In fact, you're going to have more hydrofluoric acid because you're making acid. But the whole point here is that you still have a buffer. And that pH is still going to be about 2.84. It's going to change slightly, but not very dramatically. And that's the nice thing about buffers. It maintains that pH. But if you add too much of these invader ions, so that the invader ions are in excess, you've destroyed the buffer essentially because you're going to use up all of one of the buffer components. More on that a little bit later in the unit. But for right now, just keep this idea of buffer in your mind. It contains a weak acid and its conjugate base, and it resists a big change in pH. So how do you identify a buffer? You're looking for, like I said, a weak acid with its conjugate base, or vice versa, a weak base with its conjugate acid. And those conjugates had to come in the form of another solution. One thing to note, a strong acid is not going to make up a buffer. Okay? Likewise, a strong base, not going to make up a buffer. It has to be something weak. So we have some practice problems here. Am I a buffer or not? So number one, I have HOBr. Is that strong or is that weak? That is a weak acid. And we're going to mix it together with potassium bromide. The potassium bromide contains bromide ions. And I'm looking here, is bromide the conjugate base of this weak acid? So if I knock off one of these hydrogens from this acid, or the only hydrogen, this is going to produce OBr negative. That's the conjugate base. So in order to be a buffer, this KBr had to have another oxygen in it, and it doesn't. So no, this is not a buffer because Br is not the conjugate base of HOBr. That Br is missing an oxygen. Number 2, I got ammonium chloride, and I'm mixing it together with ammonia. So I'm looking here, ammonium chloride, that's a salt. Oh, it contains some ammonium ion. Is ammonium, NH4, the conjugate of NH3? That's a weak base. Yes, NH4 is the conjugate of the weak base ammonium. So yes, this is a buffer. Number 3, HI. That's a strong acid. And I don't even care what you're putting with. Yes, I know. Yes, that is. Looks like it's conjugate, but that's strong. Cannot use strong in buffer. No buffer. Number 4, you got H2CO3. That's carbonic acid. That is weak. And I'm putting it together with sodium bicarbonate. Isolate that negative ion. HCO3 negative. Hey, that is the conjugate base of my weak acid, H2CO3. It's just missing a hydrogen. So yes, this is going to be a buffer. Number 5, I got HNO2. That is a weak acid. And look what we're mixing it with. We're mixing it with a salt solution that contains lithium and nitrite ions. And nitrite is the conjugate base of this weak acid, HNO2. So yes, you have a buffer.